My name is Tesfa. I'm the founder of the 5C app and author of the WireWalk algorithm. This video is going to be a really quick overview about what the WireWalk algorithm is. I'm assuming that you know the where-to-vec model as well as the deep walk model. Something you'll notice in the deep walk model is that when we perform our random walks, we transition to our neighbors with probability 1 over n, where n is the number of current neighbors we hold. I believe Stanford in their Node to Vec paper offered a second order random walk. Here in the WireWalk algorithm, I provide a way to rewire the graph. This is, maintain the same connections but change the weights of the edges in such a way that when you do perform your walks, you end up with richer embeddings. So I've just brought over some code from the paper linked here. I've loaded up Zachary's Karate Club. I've also set the capacity attribute equal to the weight attribute. This is necessary in order for the max flow function I've implemented to run, because it uses network X's push flow function, I believe, and that relies on your graph, your network X graph, having a capacity attribute. Moreover, I've just mapped the labels of the Karate Club graph to 0 or 1, depending on, the outcome of the scenario. I recommend, if you haven't heard the story behind Zachary's Karate Club, to look into it. And really quickly here, as you can see, I've already run this cell, and we're interested in the average F1 macro score, the average F1 micro score, the Folks-Mallow score, and the average accuracy score. Here I've just run the Node to Vec algorithm with P and Q equal to 1. This is analogous to running the deep walk algorithm on the graph. And as you can see, we get the average F1 macro score, average F1 micro score, Folks-Mallow score, and average accuracy score. Now, the Karate Club graph is probably a poor choice to demonstrate the power of the WireWalk algorithm, because something we've noticed is that when the classes are balanced, and that actually the deep walk algorithm performs better than the WireWalk algorithm. But when there isn't a balance in the classes, or when there's a large sample size, the WireWalk algorithm performs better. And so really quickly, here we'll visualize the original transition matrix. So this would be the transition matrix that the deep walk algorithm would be operating on. And then this is a visualization of all of the various transition matrix that the WireWalk algorithm offers to a random walker. So this visualizes the way that we would bias the transition matrix, where brighter colors means higher connectivity, and darker colors mean lower connectivity. These would all be features that would be captured by, say, the Tversky bias function, the Levenstein bias function, the resource allocation bias function, the Sorensen index bias function, the Salton index bias function, the hub depressed index bias function, the hub promoted bias function, the preferential attachment bias function, the LHN index bias function, the common neighbors bias function, the Adamic adder bias function, the Jaccard coefficient bias function, the min cost max flow bias function, and the max flow bias function. And then once again, here's the original transition matrix. Thank you for watching. I'll improve on this in later attempts, and please leave any feedback and questions. Thank you.